Now we're going to kind of switch gears a little bit, as Jay was saying, and talk a little about this new concept of gravitational waves. And for that, I'm going to have to work a little bit with analogies and then try to kind of bring a concept that is very familiar to you, but perhaps never told in this way. So we all know gravitational waves are things we use commonly to just get to know about our universe. As I'm speaking, my vocal cords are perturbing the air that produce sound waves, accent it all, going all the way to your ears, and that's how we get to communicate. This morning, you've seen all sort of examples of how we've been peeking at the universe with electromagnetic observations. Ever since Galileo pointed his telescope to the sky, we started learning wonderful things about our universe that both answer questions, but more often than not, open new vistas to the universe and presented new challenges to researchers. We are on the verge, on the beginning of exactly the same kind of revolution on these other sort of messengers from our universe. So just to keep an analogy in mind, let's think of this duck just paddling his way in this pond. Even if we're far from the duck and we don't even see it, we can see the ripples coming to us if we're on this kind of on one of the edges of the pond. And by understanding these ripples and how close they are, the crests, from each other, we can tell whether the duck is paddling fast or is kind of calm or whatever. And this is very much this picture we have to keep in mind when we think of gravitational waves, and as I'll describe as we go along. Of course, we can have something larger than a duck. This swan is paddling its way, and then as you can see, the seagull is just bobbing up and down as these waves produced by the swan are going by it. In its own, the seagull is not producing strong surface waves on this pond, but we can tell definitely that the swan is much more important, much more relevant in producing these disturbances than the seagull. And of course, if someone goes and skips a rock, we can tell by the shape of these waves that are produced as the rock is skipping, in which direction the rock was thrown, and how successful the person trying to skip was. So Einstein introduced a very radical idea in 1915, as Jay just mentioned, which he basically told us, let's stop thinking of gravity as an interaction that produces forces. Let's just throw that away and think of the whole universe as being a fabric. This fabric can be bent by matter or energy, as Gil said this morning. And so in this picture where we have Earth here, we imagine the fabric around Earth being disturbed, being bent by the presence of the Earth itself. And this satellite that otherwise we would have thought in Newtonian theory as going around because the Earth is pulling from it with a gravitational force, now this is the only trajectory it can go in this bent space-time. Einstein's theory has many, many radical new predictions once you buy that concept of gravity or the universe as a fabric. One of them we heard many times today, that a space that has been curved will curve everything. In particular, will curve trajectories from distant objects like a star, which as it traverses in an uncurved part of this fabric will go in a straight line, but as it comes here, it feels this curvature, turns around. And for an observer on Earth, we're going to be imagining, or we're in a picture, that the observation actually took place here, and this is this phenomenon of gravitational lensing. And this is one example, in addition to the ones you saw this morning, where we have 4 images here. They're actually produced by a star or a set of stars that are behind this center accumulation of matter that is bending the space-time here, and we see 4 images of that same object. But there was more to it. I mean, once you buy a little bit of the theory, everything comes with it. In particular, the fact that if you now have masses that themselves are bending the space-time that happen to interact, or the distribution of this matter is changing dynamically, it produces these ripples, very much like the duck paddling on the pond. And these ripples go away to the edges of the universe. And if we have the right detector, we can use these messengers to try to infer what was being produced in these ripples. Very much like the duck. Is it duck paddling faster or slower? We're going to be asking questions. What produced the ripples we see? As these ripples go around, they introduce distortions of the space-time. So the ripples will propagate at the speed of light. And things that are traversed to it get elongated in one direction, shrunk in the opposite, and this just goes in a cycle. So the poor seagull that before was going up and down, now will get squeezed from head to toe, and then elongate in the opposite, and then this thing will just continue as the wave passes through. Of course, once we want to go after them because they possess some very interesting properties. One, of course, is a new window to the universe. We want to ask questions. What is out there? And how much can we infer from these signals? There are objects, as we discussed, that can only produce signals in this channel and not in the standard channels electromagnetic that we have been using to probe our universe. So we have to ask, well, is it really worthwhile going after them? Do we have enough sources? Are the strength or the signals we have enough for us with our technology to go after them? And this is not a trivial question. It took us 100 years for technology to catch up with our imagination, or to catch up with Einstein's imagination. Because the strength of these waveforms have to do with the compactness. So how much matter have we piled up in a small enough region times that inverse proportionality with the distance. So the farther away they are, the weaker the signal or the perturbation will be. And there is also some dependence how fast the source is varying. So this is one problem we have to face. But this problem also has an advantage, which is they interact very weakly. If we were to stare up, we only see a ceiling. We don't get to see the sky because the light that is coming gets to interact very strongly with the roof of this building, and it doesn't go through. While gravitational waves just go through unimpeded. So this is a con because they interact very weakly, and it takes us a very difficult effort on the technological side to go detect them. But on the other hand, because they are so weakly interacting, they are very pristine messengers of the source that produce them. So we need to look for the strongest possible sources, and these are the ones that will have the highest compactness, because there's nothing we can do with distance. If they are far, they're far. What can we do? So we already saw in Daryl's talk that different objects that are more and more dense will bend the space-time around them in more extreme ways. So the sun does a little bit. A neutron star that is almost a black hole, but not quite, does more, and then a black hole eventually just stretches in such a large way that the most radical things in the theory arise. And once you put this number together, you can tell what is the relative changes in this distance of the size of the seagull that will be changed by these waveforms. And typically, we expect numbers of the order of 10 to the minus 19. So this is the relative change in any length that we should be prepared to measure in order to detect these waveforms. But finally, we were able to do that. I mean, the community got together, and over 4 decades, continuously improving the technology, we got to create these detectors. They are incredibly sensitive, as you will hear more in the next talk. And even with that sensitivity, the signal is buried in the noise. So we have to go from the theoretical point of view and try to help as much as we can, because what we're looking for is a needle in a haystack. And as much information as you can give to the detector of what is it that they should be looking for, the better, not only to produce a detection, to allow the detection, but also to ask what sort of needle you have. We want to use, as I said, not just the detection itself, but to understand from the detection what was the source that produced them. And this is just an illustration of some things we do theoretically to try to infer in a collision of 2 neutron stars, say, what are the waveforms characteristics. And for that, we need to bring all possible tools into the problem. Very intense theoretical calculation, exploiting the most massive parallel computers out there, and putting everything together to predict what's going to happen. So 2 of the most important or most relevant systems that we are after are systems that contain black holes, and we heard about them before as a region. So black holes is a region where nothing can escape, as they're described. They're main suspect in the most energetic phenomena that we see in the universe. Every time something goes bang with a very, very loud way, if you go deep inside, chances are a black hole had something to do with it. So they are like the bad boys of the universe. The sizes, they can go from a very few solar masses to 10 to the 10 solar masses, and they channel, as I said, some of the most intense electromagnetic energies that we have seen so far. The next kin is the neutron stars, so we've already heard about them. These are stars that have the masses of the order of the sun, but they are compacted in a region of about 15 kilometers. Just to put some interesting number with it, if I were to throw this pointer to the ground here, it would just break in pieces. The energy it gained, it will just be transferred in that collision, and we're going to get nothing. out of it that we can use, almost like a weak laser pointer. But if we were to do exactly the same exercise on the surface of a neutron star, once this thing hits the ground, it's going to release about the same amount of energy that a nuclear bomb. So what are the opportunities? And you'll hear more about as we go along, because this is a window that we just opened. We want to check whether Einstein was right. We have been writing this beautiful theory for about 100 years. But maybe at some point it will give signs of cracks. And that would be beautiful, because that will begin to point out what will replace it. We don't know if it is true. We haven't tested this far, and we're going to hear some about it today. We want to know about the origins of some of these mysterious energetic events, and in particular, if we were to collide these two neutron stars, which we know should be happening eventually, and LIGO should be able to detect them, we may even see the birth cry of a black hole. One of the possible outcomes of the collision of two neutron stars that are coming and smashing against each other at about a fraction of the speed of light is a black hole. So not only can we witness and detect what the gravitational waves are in the process, but get to see the most detailed process by which a black hole is born. So ultimately, what we want is to be able to add to these amazing observations on the electromagnetic side that we have been doing a lot of physics with, what we call the dark messengers of the universe, which we now know as gravitational waves. It's a complementary window to the universe, and the combination of the two will give us amazing things. Just to give one example, we heard this morning about transients. And Vicky said, when you look at transients, you don't know where to look. You just point and hope that something is going to happen. And luckily, nature always gives something interesting. But now with gravitational waves, as these two objects are coming together, as you'll see in the next talk, we're going to have waveforms from very early epochs till the merger takes place where we have the main bang. It would be a very interesting possibility of using gravitational waves to warn, to tell us when and where to look, because the fireworks are about to start. And this is one of the most exciting possibilities and some of the things that we've been doing active research on. And with that, let me stop, and thank you.